we have seen that if I'm faced with a rational function, that is a polynomial divided by another polynomial, that the method of partial fractions is a little bit of algebra that allows us to convert messy rational functions into these really nice sums of simpler rational functions that we know how to deal with. However, all of the techniques that we've seen before depended on the fact that the degree of the numerator was a smaller number than the degree of the denominator. What I mean by degree is just the highest power of x that occurs. So in this case, the numerator has a power of 4 and the denominator has a power of 2. Since 4 is a bigger number than 2, the old methods don't apply. That this is one where the degree of the numerator is bigger than the degree of the denominator, and we can't just immediately go and apply the method of partial fractions. But what we can do is something called polynomial long division. And polynomial long division is going to be able to take this rational function and write it as a polynomial plus a rational function where the denominator is a higher degree than the numerator. So we're going to be able to sort of decompose it as this polynomial and this rational function that does apply the methods of the previous video. So the way we do this is kind of just the same thing as we used to do just with normal long division. I'm going to first take the numerator. So the numerator is x to the power of 4th, and I'm going to put a few zeros in here. I've got a 0x cubed, I've got a 0x squared, I've got a 2x, and I've got a plus 7. So this is the numerator, but I've sort of filled in every power of x here with the proper coefficient. And then I take the big dividing sign, and I'm dividing this by x squared plus 3x plus 2. So the way we can think about this is just like normal long division. Normal long division, we've just have the ones column, the tens column, the hundred column, the thousands column, and so on. It's just that here we have the ones column, the x squared column, and so on. It's more or less the same thing. All right, so we have an x squared. We need to get up to an x to the 4th. So what I'm going to do is I'm going to put an x squared up here. So x squared multiplied by x squared plus 3x plus 2 is going to give me x to the 4th plus 3x cubed plus 2x squared. And what I'm going to do is I'm going to take the top row and I'm going to subtract it off of the bottom row. And this is going to give me, well, x to the 4th minus x to the 4th is just 0. So I'll put a 0 here. 0x cubed minus 3x cubed is minus 3x cubed, and then minus 2x squared. All right. So now I want to get a term of the form minus 3x cubed. So I've got an x squared already, so I'm going to do a minus 3x. And that's going to give me minus 3x cubed minus 9x squared minus 6x. Again, I'm going to subtract these two things from each other. So this is going to be subtracting off all of that. The minus 3x cubed minus the minus 3x cubed is just going to be 0. Minus 2 minus a negative 9 is like plus 9. So this is going to give me 7x squared. And so if I take the 2x from the top, I subtract off this minus 6. That's going to give me a plus 8x. And I may as well bring down this plus 7 from the top as well to keep everything looking nice and clean. Okay, final thing. Now I have to deal with a 7x squared. I've got an x squared, so I've got to add a 7 to this. This gives me 7x squared plus 21x plus 14. So subtracting 7 minus 7 is 0. 8 minus 21 is going to be minus 13x minus 7 minus 14, so minus 7 down here. So now I have 13x minus 7. This is a smaller degree than the x squared. That means I am done. I have everything. And here is our grand conclusion. It is this. It is that our fraction that we began with, this x to the 4th plus 2x plus 7, all divided by x squared plus 3x plus 2, that big mess is equal to the x squared plus 3x plus 7, the polynomial x squared plus 3x plus 7, plus this remainder term, the minus 13x minus 7, divided out by the denominator, x squared plus 3x plus 2. Or in other words, when I do my polynomial long division, I get one polynomial, this x squared plus 3x plus 7, and and then I get a little bit left over. That's still divided by the denominator. That's my remainder. So the minus 3x plus 7 divided by x squared plus 3x plus 2. And then the key point is that this rational function I have on the right-hand side, that is just going to be something I can use the method of partial fractions for. So copying and pasting the answer that we had, the original function has now turned into this one. And this is something that's relatively straightforward to do. The left of the two integrals, this is just a polynomial, it's completely trivial. The right of these two is one that we're going to have to use a little bit of integration by partial fractions on, so let's go and do the right-hand integral and then we'll put it all together at the end. So I'm going to say that minus 13x minus 7 divided by x squared plus 3x plus 2, well, I can factor the denominator like this. This is minus 13x minus 7 all divided by x plus 1 times x plus 2. So what we're looking for, this is two distinct linear roots, is I'm trying to find an a divided by my x plus 1 as well as a b divided by my x plus 2. And if I'm going to multiply both sides of this equation by the denominator, multiply both sides by x plus 1, x plus 2, what that's going to give me is minus 13x minus 7 is equal to a times, well, the x plus 1 factor cancels, so I'm just left with x plus 2. And then plus b, well, the x plus 1 factor now, or excuse me, the x plus 2 factor is going to cancel, and I'm just left with x plus 1. So a shortcut that works really nicely for distinct linear roots like this, doesn't work as nicely when they're going to be repeated or irreducible, but it works really nicely in this case, is I can just plug in some of these numbers. So plugging in the x equal to minus 2, I have a plus 26 minus a 7, and so this is going to be a plus 19, is equal to, well, the a term is just going to be 0 when I plug in minus 2, and then plus b multiplied by minus 1, and so b is equal to minus 19. Likewise, if I plug in x equal to minus 1, I'm going to get 14 minus 7, and therefore I'm going to get 7. I'm going to have this being a multiplied by minus 1 plus 2 is just 1, so just equal to a, and then plus b multiplied by 0, so in other words, my a is just equal to 7. So I've computed what my a and my b are going to be, and so returning all the way back to my purple, so doing the first of these, the polynomial, that's the easy one. X squared goes to x cubed over 3, plus 3x squared divided by 2, plus 7x. So that's just dealing with the left-hand side, which is straightforward. Now the interesting side, this is going to be the integral of 7 divided by x plus 1 minus 19 divided by x plus 2. And all of this dx. And so what do we get? Copying and pasting. The polynomial we've already evaluated, don't need to do it again. 7 divided by x plus 1, I set my u to be x plus 1. My du is just going to be dx. So that all works out. It is 7 ln of the absolute value of x plus 1. Likewise, for the next one, the minus 19 comes along for the ride. The denominator is 1 over x plus 2. I set that to be my u. And so ln of x plus 2, all plus c.